Everyone around the world, welcome to this Black Hole PIRE webinar. The Black Hole PIRE project, or the Black Hole Partnership for International Research and Education, is a U.S. National Science Foundation funded project to support the science utilization of the Event Horizon Telescope. Our contributions include from instrument design, data processing, theoretical simulation, testing general relativity to training and education. So this webinar will continue this year's theme on computation. So before we start, let's go through some housekeeping items. So first, for other panelists, please make sure that you mute. I will mute myself after this intro. For the webinar attendee, please open up your Q&A window from Zoom so that you can type in your questions during the webinar. We will monitor the questions and answer them when appropriate. The presentation will last for about 15 minutes, and there will be a bit of time after that for answering questions. So today's speaker is Dr. Lisa Perez. She received her PhD in physical chemistry from Texas A&M University in 2002. She led the laboratory for molecular simulations there and is currently the director for the Advanced Computing Enablement and Associate Director for High Performance Research Computing at A&M. She's a co-PI of ACES, Accelerating Computing for Emerging Science project, which she will describe today. So Dr. Perez, please take it away.
Good morning, everyone. Thank you for that introduction, CK, and for the invitation to speak at the Black Hole PIRE webinar series. So today, what I'm going to be talking about is our NSF-funded ACES system, along with some of the other more traditional HPC systems that we have available at Texas A&M University under high performance research computing. So I will start by focusing on the innovative composability at the hardware level that we have for two of our systems, both FASTER and ACES, and how we envision those platforms and the hardware composability being able to transform scientific workflows. So just as an overview, in high performance computing, an architecture comparison. So we have legacy HPC, which is prevalent everywhere for high-end computing, and the legacy HPC is built on converged hardware. You have a static hardware design, the GPUs and accelerators are fixed in their configuration, you have fixed memory and fixed storage. And the only way that you can change your configuration is if you actually go in and physically change the hardware. So maybe buying new servers, possibly buying new accelerators and having to plug them in directly to the servers and things of that nature. Modern HPC will be built on disaggregated hardware. So instead of having a fixed server platform where you have the motherboard and the accelerators directly plugged into it and the memory directly plugged into it, maybe some kind of global storage, what you will have are this disaggregated hardware that's available, pools of resources, pools of your accelerators or GPUs, pools of memory, pools of storage. And with the modern HPC, when you need to change the configuration, you're no longer having to move the hardware around, it's at the software level. So I want to introduce you to some of our traditional clusters that we have, and then we're going to compare that with our composable clusters. So here are three of the systems that we currently have built on traditional HPC. We have our flagship system named Grace. We have 925 nodes, 48 cores per node, and we have a number of GPUs that are available on the system. We have NVIDIA H100s, RTX 6000s, T4s. We also have some large memory nodes. And it's connected together with InfiniBand with global 8.9 petabytes of raw storage. And then Terra is our slightly older system with 370 nodes, 28 cores per node, and some older GPUs on it. And we have a compliant computing system named Vital, and this has some V100 GPUs on it and large memory nodes. So what I want to point out here for this is that this configuration, we had to design it before we purchased it, and then we purchase it, and then we accept, we get it installed, and then that configuration is static. Workflows change, but the configuration stays static. And while Grace serves the needs of many, many users and their research that they need to perform, what we envision is the composable systems will be able to adapt to new and novel workflows without having to purchase a new system. So for our traditional HPC, as I mentioned, Grace is our flagship system. And what I want to point out here are the accelerators that are on the compute nodes. So we have 148 core GPU nodes, and each of those have 2 NVIDIA H100 GPUs in them. So they are physically plugged into the motherboard by the PCI Express. Okay, and so that is a static configuration of those GPUs. If you need more than, if we get new workflows that need more than 2 A100s on the server, the motherboard, we would have to buy something new and plug it into our HPC system. We also have the 2 RTX per node. We have 9 of those. And then we have nodes that have 4 T4s. But again, these are static configurations. So once you purchase the hardware, once the hardware is installed, that's the configuration that you have. And if your workflow needs something else, you have to go to another system. So this is just a diagram illustrating traditional HPC PCI. So what I mentioned for the Grace system is that we have 2 A100s directly attached to the motherboard in a compute server. And we have 100 of those nodes. And this is just a diagram showing that, something along these lines. This is not specifically for our system. This is an NVIDIA diagram of a PCIe connections between the GPUs and the CPU. So there are these PCIe slots, and those PCIe slots direct the traffic from the GPU to the CPU when needed and between 2 GPUs, okay? And it has to go through the PCIe. And for some of you, you may also know that when you have GPUs, you can do something a little more direct where you have NVLink. And that adds additional connectivity between your GPU accelerators. So it doesn't have to go through just the PCIe bus that has a slower connection. You can do direct connection through the NVLink between the GPUs. So these PCIe paths are static in traditional HPC. It's on the motherboard. The GPUs are directly attached to it. And then you either take those PCIe connectivities between the GPUs, or you have the NVLink, which has the faster connectivity between the GPUs. And we'll talk more about how that differs when you move to composable architectures at the hardware level. So I'd like to talk a little bit about traditional composability. So the word composable systems has been around for a while, and it's used in different ways. This is a very broad umbrella about using what are referred to as pools of resources. So with traditional composability, you often think about the cloud. The cloud is highly composable. They have large pools of resources, but the vast majority of those resources are built on traditional architectures and traditional HPC for their high performance computing. And what they do is they allow you to choose the resources that you need, and then they aggregate them in different ways. So I've just put an example here. This is from AWS, huge cloud provider for resources, and chose accelerated computing. And I want to point out here that it says virtual CPUs. Okay, so when it says virtual CPUs, what you're getting is generally part of the CPUs that are available on the motherboard, the server, okay? And you may be getting all of them, but there's a hypervisor in between that is controlled at the software level, and it is determining how many of the resources that you're getting for the system. So in traditional composability, what's usually the case is that you are getting part of a motherboard, okay, or you're getting part of their HPC and you're designing what you need, but you're not actually building from disaggregated resources at the hardware level a bigger compute node. And we'll talk more about that, but that is the major difference between what we consider to be most of the composability that is out there and what I will be focusing on for our FASTER and ACES systems that we have at Texas A&M High Performance Research Computing that is built on the hardware composability. Okay, so the other composability that you get in the cloud more often than not is being able to compose the storage. So they have very specialized ways of being able to compose that storage so you get better performance. Another level of composability that you regularly hear about is building Kubernetes clusters. So for Kubernetes clusters, you also have pools of resources, and you use the Kubernetes software platform to generate your own cluster based on those pools of resources. So there's a bunch of different types of compute nodes that might be available. You may be just pulling in a small number of resources from a single compute node, like you might do in the cloud, where you don't need all of the resources on a single compute node. You may only need a certain number of the CPU on it, a certain amount of the memory, and then it partitions that off so that you only have access to that. Or you may be taking the entire node and you need 4 of those nodes that are available from your pools of resources. And then you build your own HPC, your own high performance computing cluster, or whatever type of cluster that you need, using the Kubernetes software. And so it will give you at that software level your own system where you have those nodes available so that you can run your specific research workflow. But again, this is taking traditional hardware, okay, and then you're designing what you need based on those pools of resources that are available within the constraints of the traditional hardware that you have available to you. The traditional compute nodes, you may be parsing it up, but you're not building a compute node that can be bigger from disaggregated hardware. So now let's actually talk about composability at the hardware level. So this is what we've been talking about is traditional servers. And you might have some composability at the software level, you know, taking small amounts of these traditional servers, or maybe taking the whole thing and having maybe building on a little bit of storage to it, something along those lines to support your research workflow. When you have composability at the hardware level, you have truly pools of resources. So you have your server pool, which are your compute nodes, okay? And those are generally the same as what you think about in a traditional server configuration, where you have your CPU and your memory directly attached. Okay? But then you also have an accelerator pool. So you can have GPUs, FPGAs, and we'll talk more about what accelerators are supported in the type of composability at the hardware level that we have on FASTER and ACES. You can have storage pools. So you have these composable resources, and then you have some kind of a fabric that can take these disaggregated resources and compose them to the server that you need. So once you compose, you can have, to within a certain degree, whatever resources you desire. So you have your server, and then you attach those resources. So here I have 3 accelerators, and I've also added on some SSD storage. And this can also be used as memory using something called memverge, which I'll also talk about a little bit later. And then we have another one here where I've attached 1, 2, 3, 4, 5, 6 accelerators and an SSD. Okay, and as you can see, I have another server where I composed 1, 2, 3, 4, 5, 6, 7, 8, 16 accelerators to my server. So that means for this configuration right here, the operating system sees all 16 of those accelerators as if they were directly attached to the motherboard. Okay, and we can go up to 20 accelerators with our current deployment on Faster. And if anybody in the audience has done any programming, you know that programming for having your accelerators directly attached to the motherboard, the operating system sees them directly attached to the motherboard, it simplifies the programming. And then in general, for traditional HPC, you often see speed up when they're directly attached to the motherboard, because the communication is faster between the GPUs. So on our systems, we use Liquid for our composability at the hardware level. There are other providers that are out there, but I'm mostly going to focus on Liquid since that's what we have on our systems. So what you have with the Liquid architecture, you have, or the Liquid software and hardware, you have a command center, and that is what lets you control composing your resources. And here is the hardware breakdown of what physically is happening with the actual accelerators, servers, and so forth. So we have the Liquid Fabric switch, right? We have a bunch of compute. You may have a pool of NVMe available, a pool of GPUs, one of the accelerator types, a pool of Optane SSDs. You could have a pool of FPGAs and other accelerators. And then here we can also have composability of NICs, so network interfaces. And then here I'm just illustrating some of what the command center looks like. So this is one of the fabrics. So if you'll notice, oops, on my previous slide, I said, here's the Liquid Fabric. So within this fabric are the pools of resources. And you can take those pools of resources and choose what you want to create for your machine. So your server and how many accelerators and different types that you want on that server. So this is what the actual hardware layout looks like, and this is what the software interface looks like. So let's go a little bit deeper into composability at the hardware level. So this is a schematic diagram that shows the connectivity between the server nodes and the PCIe devices, our pools of resources. So what we saw in the previous diagram, I said that there was the Liquid Fabric, right? The switches that are available, and then those pools of resources. So these would be the server nodes, and these are the PCIe switches, and these would be the PCIe devices that you can compose to make your server that you need for your workflow. So here we have PCIe devices can be GPUs, FPGAs, SSDs, and basically if it's a PCIe device, then you can plug it into one of the expansion chassis that can be composed to the compute node through the Liquid Command Center. So one of the other things that I want to focus on here is that these pads. So we have the server nodes and they're connected to the PCIe switch, and inside the PCIe switch are some chips. And those chips control the communication. So when you have your server and it needs to communicate with a PCIe device, it goes to the PCIe switch, moves through whatever chips it needs to get to those PCIe devices. Okay. So in a composable architecture, in a hardware composable disaggregated infrastructure, what you have is the servers communicate through these PCIe switches to go to the device. Now, if you recall when I showed the diagram that was showing the PCIe paths specifically for an NVIDIA kind of DGX with NVLink and a server with NVIDIA A100s directly attached to the server. Those PCIe paths are static. They never change. But when you have composability at the hardware level, when you recompose, your PCIe paths are going to change. And you will be sharing the fabric for those PCIe paths. So even the PCIe paths are not static. They do change as you recompose and design your new servers. So one of the other things that I want to talk about, which is going to be very exciting when we get to CXL level 3, which is not quite here yet, but hopefully is on the horizon, is composable memory. Now there's composable memory today, but it's not fully pooled and shared composable memory. We're at CXL1 and CXL2. We do have some sharing of the memory, but this is where we really want to be for truly composable memory at the hardware level, which is a great importance when you have a substantial number of accelerators, you're doing large scale AI ML. If you're doing, anything in the genomics realm, you usually have to have a large amount of memory on your server to support the workflow that is using a large number of accelerators on a server. So now that we've covered some basics of traditional HPC, traditional composability, and composability at the hardware level, I want to focus on a better description of the two systems that we have that have composability at the hardware level. So FASTER, Fostering Accelerated Scientific Transformations, Education and Research, is an NSF MRI funded system that we have at High Performance Research Computing. This also has the liquid PCIe Gen 4 composability fabric. We have 64 cores per node on these systems, and we have a pool of NVIDIA GPUs that are composable. So we have 200 T4s, 40 A100s, 10 A10s, 4 A30s, 8 A40s. And if we decide that we need a different type of GPU, we always have the option to plug in different GPUs in the expansion chassis. And then, of course, we have a good interconnect between the nodes to support HPC and global storage. Okay, but the important thing here is that we have these pools of composable NVIDIA GPUs so that we can design our compute nodes as needed for our researcher workflows. So this is just an example of some of the benchmarking that we've done to show that the PCIe composable architecture doesn't take a performance hit compared to traditional HPC or performs as good or better than traditional HPC. So we've done some Horvath TensorFlow benchmarks on FASTER and Grace. So FASTER is our composable at the hardware level system, and Grace is our traditional HPC. And we get good performance on both systems, quite comparable, so that we've satisfied that our PCIe fabric is scalable. So if you remember on the composable architecture at the hardware level, it's going through the PCIe switches, it has to go through the chips and taking different paths to the different accelerators. So we've done up to 16 GPUs in comparison on a single node using A100s and compared that with the multiple nodes on the Grace system to ensure that we are getting good scale up, even on the PCIe fabric. And then we also have, these are this is a traditional calculation using LAMPS, which is an atomistic simulation with up to 33 million. We do start seeing some performance hit here, going above 8 GPUs, which 8 GPUs is a more traditional HPC. So we are looking more into this to see if it's more at the model level as opposed to the PCIe fabric level. We've also performed a number of scaling calculations on just the CPU to ensure that the PCIe fabric is not affecting our CPU and communication with the other compute nodes when you do not need to use the accelerators. So this also helps to make the usage of the HPC system more efficient. The people that need accelerators can use the nodes where we've composed accelerators, and then the CPU nodes are available for those that just need to run CPU workloads. And that way the accelerators are being used efficiently and the CPUs can be used efficiently. So we get good scale up when comparing with both Grace, and Faster does have a faster CPU on it, so it is not surprising that we get better wall clock times. Okay, so Faster was the first system that we got with the hardware composability with liquid fabric. ACES is our system that is currently on the floor, powered up and being configured, not quite ready for researchers to hop on, but I'm close to getting there. So this is also an NSF-funded system through the ACSS. We named it ACES, Accelerating Computing for Emerging Sciences. And we designed this system as a test bed with a large number of different types of accelerators for researchers to develop novel, new scientific workloads. So it's a test bed designed for AI/ML, but can support many other workloads. And again, providing large number of accelerators so that you can have new development and you're not limited by the standard accelerators that are available in an HPC environment generally. So it's just a map of the NSF-funded advanced computing resources. Here we are down here, ACES in College Station at Texas A&M University, and we're part of the innovative system, which are all listed here in green. And then we have other resources that are part of this ecosystem to support your computational needs, leadership class systems, cloud resources, shared campus resources. So what will we have available on ACES? ACES has been deployed in 2 phases, be more like 3 phases, sorry. But phase 1 incorporated Graphcore IPUs, Intel FPGAs, the D5005, the Intel Max GPU, the predecessor to what is released. This is under NDA, and Intel Optane SSDs. So I will talk more about each of these. These were originally available through Faster. We plugged them into one of the expansion chassis so people could have early access to them before we had the full deployment of ACES. ACES phase 2, which is what is happening right now, is where we have Intel Sapphire Rapids CPUs. These are 96 cores per node. Again, includes the composable infrastructure. So this will be the next generation of Liquid's composable infrastructure. We can compose up to 20 PCIe devices per node. And all importantly, Faster also has this, is that we have data transfer nodes. A lot of the scientific workflows ingest data. So if you have, information coming in from collecting your astrophysics data or from any experiment, being able to transfer that data in quickly and performing calculations using the accelerators is very important. So we have the data transfer nodes for that. So ACES phase 2 also has the Graphcore IPU. Everything from ACES phase 1 will be moved over to ACES phase 2 once we completely get online. Have the Graphcore IPUs, which again, I'll talk about more. We'll include the Intel FPGAs and newer FPGAs. These are also based on the Intel chip. They're provided by Bitware. So the next generation of the Intel FPGA by Bitware. NextSilicon coprocessors, NEC Vector Engine. The Intel Max GPU was formerly named PVC, Ponte Vecchio. We will have NVIDIA H100s and Intel Optane SSDs. Most of these will be composable, not all of them. So the Graphcore IPU is not a PCIe device, so it is a standalone. The Intel FPGAs, the NextSilicon, the Intel Max GPUs, NVIDIA H100s, and the Optane SSDs are PCIe devices, so they will be composable on the Liquid infrastructure. The NEC Vector Engine, at this point in time, may or may not be composable. It is a PCIe device, and I'll talk a little bit more about that in just a little bit. So what kind of research workflows can we support? We compiled a list of some of the scientific workflows or applications that can be supported by these accelerators. So for the NEC Vector Engine, you can have AI/ML, supports chemistry workflows, VAST, quantum espresso, earth sciences, NumPy, oil and gas, plasma simulations, weather, climate simulations. And this is just a subset of the actual applications and workflows that could be supported, just to give you an idea. For the Graphcore IPUs, it's mostly focused on AI/ML workloads, where you're using traditional, Python implementations of PyTorch, TensorFlow, to do, graph data, neural networks, natural language processing, okay, for a lower energy footprint. The Intel Bitware FPGAs, AI models, big data. There's a lot of possibilities for the FPGAs. It's heavily used in genomics for very specific tasks. When the data is coming off of the instrument, it gets ingested and processes very rapidly. MD codes, streaming data analysis, compression is often used on the FPGAs. And, computing at the edge. When you have to compute at the edge, FPGAs are often used for the lower energy. We will have the Intel Optane SSDs. These can be composed as storage, but they can also be used as memory to supplement when you have a number of tasks that need to be performed. And those tasks require a combination of hot and cold memory. You can run multiple tasks as long as you don't dip into too much of the hot memory. So the Intel Optane SSDs with the MemVerge, which I'll mention a little bit later, is more focused on running multiple tasks and providing extensive cold memory so that you can run more of the workflows than you normally would be able to. And NextSilicon is very exciting. It has some software layer that will let you compile your codes and utilize the NextSilicon accelerator, which is an emerging technology to run your workflows and do an analysis, and it will adapt to the workflow to try to accelerate it. So it can be used in a wide variety of applications, molecular dynamics, some computational fluid dynamics, and so forth. Okay, so as I mentioned, the Graphcore IPU While we have it in our composable infrastructure, this is one of the ones that we cannot compose, but I wanted to mention it because it is a very nice technology for your AI ML workflows. It performs those tasks at a lower energy footprint than your standard accelerators. And the way that it is designed is you have, comparing to standard CPU and GPU architecture, you have large chunks of the memory, and you can easily run out of memory on your accelerator. If anybody's ever experienced that when running your large AI ML workflows, you can run out of memory on your GPU. And then you have to have more GPUs, you have to go off the GPU and communicate with the CPU and the memory. With the IPU, it's very fine grained. Okay, so communication between the compute and the memory. So it's very tightly coupled, but that does mean that you have to, well, it's the same thing for the GPU accelerators. They provide an interface to the standard TensorFlow and PyTorch workflows to run on their IPUs with minimal modification to your code. So we've done some benchmarking there just to show that the IPU, this is pairs of IPUs compared to using 8 of your more traditional accelerators, and you get good performance with the IPUs. Again, this is based on a lower energy footprint than the standard accelerators that are out there. And you can read more about that, and these slides will be provided to you in our publication. We also provide quite a bit of training. When we have a testbed system, it's critical to provide training to the researchers so that they can utilize the novel hardware. So we have a YouTube channel that posts most of our training sessions. And we try to have our training set up so that it's a very hands-on approach. So we have an introduction, and we always want to have strong hands-on components so that you can really get in there, test out the architectures, run some workflows so you get a feel for how it works. So I want to mention for our Intel FPGAs, and this is true for the bitware also, we have the Intel Sapphire Rapids CPUs, the Intel FPGAs, the D5005 and the upcoming bitware. And then we're also going to have the Intel Max GPUs. And one of the unique things that Intel has right now is in their One API suite, they support the XPU. So with One API, you can design your code so that it will run on both the CPU, their FPGAs, and their GPUs in a seamless fashion, so the XPUs. Now, there's some development involved in there, so you do have to modify your code, but that modification is streamlined in One API. So if you have an FPGA or you have a workflow that runs on the CPU with One API, and you feel that it would benefit from using an FPGA, you can modify your code with the One API, adding in some directives to also run on the FPGA, and then make some other small modifications to run on the Intel GPU. So that is the goal of One API, is so that you can have more of a hardware agnostic compile, and you can run on the XPU or specialized accelerators. So as an example of some of the things that have been designed for the Intel FPGA, fast Fourier transform is always a strong focus. Runs very quickly on the FPGA. CP2K has a plugin for running the quantum molecular dynamics using the fast Fourier transform algorithm on the FPGA. So it offloads it to the FPGA. I want to give a shout out to our host, CK, who's been working with us and developing on our FPGA that we had in ACES phase 1 and what we will have in the newer one in ACES phase 2. He's been working on the N-body problem and developing an algorithm that will utilize in an efficient fashion the FPGA and then CPU and GPU using the one API, focus on XPU development. So I know I'm talking a lot about the different components, but please keep in mind that these components are on the PCIe fabric, so that if you have a research workflow that could, part of the workflow may be doing inference and you want, a accelerator that is good for inference, or you're running something that wants to use the FPGA, another part of your workflow, maybe another part of your workflow is just CPU based, you can take these different accelerators and we can compose them to the compute node so that you have different types of accelerators or multiple of the same type of accelerator or no accelerators in these composable HPC systems at the hardware level. And so I mentioned that we had those PCIe-based SSDs that we can compose and use as storage directly, or we can use them as memory using Memverge memory machine. So we ran a quick test with using HPL with these composed and going a little bit above the memory that's available on the system and dipping into the Memverge. And we do see a little bit of a performance hit. So as I mentioned, with the Memverge memory machine, what it's really designed for when using the Intel Optane SSDs is if you have a research workflow that spawns many tasks, and those many tasks or those many independent calculations like to cache a lot of memory, but only use the hot memory and just dip into the cache memory. This will allow you to run more of your computations on the node with the physical memory and using the SSDs for that cached memory. So if you have that type of workflow, again, this is where the training comes in, where we teach the researchers what types of workflows work best with the different accelerators that we have and the Memverge memory machine with the composable Intel Optane SSDs. So if you are interested in getting on ACES, this is for ACES Phase 1. We haven't opened up ACES Phase 2 as of yet, but you can apply to get on ACES Phase 1 by going to this webpage, and there's an application form that you have to fill out. We are in the transitionary phase, so the Graphcore IPU is being moved off of Phase 1 and onto Phase 2 and will be unavailable for just a little while, but we do have still the FPGA and the Optane SSDs that are available in Phase 1. For Phase 2, you will apply directly through ACES. So you'll see here that you must have an ACES account. This is the NSF-funded ACES system, which has replaced Exceed. If you're familiar with that, you can apply for an ACES account. This is where you would go to get ACES Phase 1, and when it becomes available, when ACES Phase 2 becomes available, you would apply for it directly through ACES. And if you have any questions about that, please reach out to us, and more than happy to help you get an account. So once you have an account, you want to test out these systems, we do provide an easy to access portal. If you go to our webpage, you'll see a portal drop-down menu, and we have portals available for all of our systems. This is the Open on Band portal that we have modified to fit our needs. This would be for the TAMU researchers, and as an external user, you would be coming in through ACES. So right now we only have FASTER listed. Remember, ACES Phase 1 is part of, it's in the FASTER liquid infrastructure accelerator pool. And once we get ACES online and we start adding people in, you'll see an ACES listed here and you'll log in directly there. So it's an easy to use interface, gives you lots of options on how to spawn your research workflow through a standard web browser. So we have this, infrastructure at the hardware level where you can compose it at the hardware level, design it for your research workflow needs. We need to make that easy for the researchers to use. So we provide the portal that makes it easy to access. One of the other things that we've developed is what we call the TAMU dashboard for Texas A&M University. This is part of the Open On-Demand portal, and it's just a one-stop shop that shows what is going on the system and what's available in your account, a summary of your allocations, your jobs, and analysis on those jobs. And you can read more about the TAMU dashboard in our publication here. So what we have here is cluster statistics for what's being used on the system. You'll notice this is Grace. We're still updating it for faster. It will be available very soon. Ran into just a few issues on that with the new operating system. It will definitely be available on ACES. A summary of your accounts, and more importantly, your jobs. So if you want to see a summary of what happened when your job finished, you can click on the summary and it shows a log of what was utilized during your simulation. So the post-analysis is very important so that you understand what resources it used. We already have lots of software installed. You can go to this webpage, type in your favorite software. You'll probably find that we already have it installed. If we don't, you can put in a request to install it through the portal. So with the composable system at the hardware level, the way that it is set up at the moment is that we already have pre-composed a number of compute nodes with accelerators composed to those nodes. And then you use it similar to a traditional HPC system. So the user doesn't really have to know about the underlying composability. When I showed you the Liquid Command Center, the administrator is the one that has access to that to recompose the nodes. So as of today, the way that it works on Faster is that we have statistics on, the most commonly used configurations. We've composed those. When a user needs a different configuration for their workflow, they can put in a request and we can recompose the nodes for that request. In the upcoming systems, it should be a little bit more automated, where we can do a little bit more recomposing without having to go in and manually change things. But that is upcoming, and I'm looking forward to presenting on that once we get ACES completely online. Okay, so for the end user at this point in time, we have PE-stat is one of the, we have the Slurm queuing system on both Faster and it'll be on ACES. And you can use the PE-stat command listed here to show what the current nodes that are composed and their state. And this way the user can set up their job file for current configurations. And if they don't see the configuration that they think they need for their workflow, or for their testing, again, you can just put in a request to have it reconfigured, and we can do that and reconfigure the node to have the accelerators that you need to design your workflow. We've also made some additional utilities to make it easier for the end user to determine GPU availability. So this is just a script that will check the current nodes that are available and what might be available to use. Now, using these composable systems in the Faster and ACES environment is very similar to running on a traditional HPC system. You generate your job file, ask for the resources that you want in one of the current configurations, and then you submit your job and run. And again, if we don't have the configuration that you need for your research workflow, you can put in a request to have that changed. So I did mention that we have quite a bit of training that occurs, and we post those trainings on our YouTube channel. We have a wide variety of of resources available in videos on different topics on our YouTube channel. So I would encourage you to visit that. You can go directly to our main page for HPRC, and we have a YouTube link, or directly to the YouTube channel. And we have 865 subscribers, and we haven't really done much of anything to get those subscribers, so it just happened organically. So the last thing I want to mention, because I know we're definitely getting close on time, is, composability at the hardware level. What we envision is that it will enable transformative scientific workflows. Okay, and I'm just, giving examples of workflows that are out there. So for, the laser interferometer, gravitational wave observation, so LIGO, you have the detectors, it sends data over, you go through a bunch of different workflows that are needed, okay, and then you come up with your results. So we want to support those workflows, but we also want the researcher to be able to only be limited by their imagination and the software available, and not be limited by the hardware. So we want to provide that hardware in a composable fashion so that you can design the most optimal scientific research workflow that would enable science you wouldn't be able to do otherwise. And this is where we want right here, is in this computing hardware. We want the hardware not to be your limitation. And that's where we feel that composability at the hardware level, with a pool of accelerators and resources, is going to be highly transformative. So I want to thank everyone for listening, and I'll go ahead and open it up for questions, or if we have anything in the chat. Oh, and I do want to mention that we do have a end of presentation survey. Please fill it out. That feedback is very important to us, so that we can provide, very important to everyone, so that we can provide better resources for everyone in these webinar series. Thank you.
Thank you very much, Lisa, for the wonderful presentation. So I guess, for everyone, if you have a question, feel free to type that in the Q&A, or you can just raise your hand, and then I will allow you to talk, so we can have more interaction. There is actually a question already at the Q&A that I try to answer, and Lisa can correct me if I answer it incorrectly. So the question was from Simon. So it is about, so all these fabric connect to the accelerators through the cloud. So
No.
That,
I'm sorry, go ahead, finish. I cut you off.
No, that was
the
the question. That was the question.
Okay. Well, I don't know, cloud to me is a very broad term, but all of this is on-prem hardware. So it is in our server room. I mean, I guess you can kind of think of the PCI switch as cloud, but it's all on-prem hardware. It's all in the racks. It connects to the accelerators through our PCIe switches that are in the racks with the chassis that have the accelerators. So I wouldn't really call it where you are accessing accelerators that are in the cloud, because they're not part of that liquid PCIe fabric. Let me know if that did not answer your question. I can expand more.
So there's another question coming in. Sorry, I got confused. Is it true that you can only use configurations that are pre-made, and the end user cannot compose their own nodes and PCIes?
That is a very good question. And yes, everything is confusing. It's a whole new world, and especially with the word composable, it covers a lot of different topics. So what we have right now on Faster is that we have pre-composed compute nodes based on standard workflows that are utilized on our systems to best fit the needs of our researchers. But we have the ability to recompose them. As an end user, you cannot do it. You have to request to have a node that is recomposed with what you need for your research workflow. In the future, the goal is that you will not have to put in a request. You will just be able to specify the resources that you want, and it will automatically compose that node for you. We're just not quite there yet. We have the flexibility to change the configuration, but the user has to put in a request and the system administrators have to do it.
Okay, thank you. I think that is very clear. Is there any more questions? Again, feel free to raise your hand and I can unmute you so that we can just chat. So while we are waiting for a question to come in, myself has one on the different accelerators. So Lisa, you mentioned for the Intel accelerators, we can use the one API to program the different accelerators. But how about the accelerators from other companies? What are the programming model? Does each of them has a different language or library to use?
Yes, that is a very good point. So NextSilicon has their own compiler. Vector Engine has their own compiler. Graphcore IPU has the implementation of, PyTorch and TensorFlow. What else am I missing? So for all of the new novel accelerators, they generally have their own compiler. And so you would need to use them. It's only the one API. If you're going to program for, you can use one API for the Intel-based accelerators, and then of course, one API with or CUDA for H100. But yes, most of the new novel accelerators or other accelerators have their own compilers.
Okay, I see. All right. Any additional questions from the attendees? Well, if not, then I guess we are right on time. So thank you again, Lisa, for the wonderful presentation. And for all the attendees, please fill in our survey. It's very short, but it's important for us to improve this webinar. And then I also see our project manager, Rosie, put in a link to the Black Hole PIRE YouTube channel. So this presentation will also be posted in that YouTube channel. Thank you, everyone, for attending.
Thank you.
Bye.
Bye.